In the previous lecture, we talked about how we can produce induced current. According to Faraday's law, we can produce current by changing the flux passing through some closed loop, like in this picture shown here. There is a closed loop that is connected to a light bulb, and when you rotate this closed loop in some magnetic field, there would be change in the flux passing through the closed loop, and as a result there would be current produced in the loop, and with that current you can light a light bulb. Okay, so the basic idea here is, again, we have this magnet has two poles. It could be a north pole or south pole. Let's say this is a north pole and this one is south pole. So we have the magnetic field lines going from north to south like that. Okay, and so the flux passing through this closed loop, we have this loop between the two poles of the magnet, and the flux passing through that is phi is equal to BA cosine theta. And like we saw last time, when we change either B or A or theta, we change phi. Okay, and when we change phi, we produce EMF, and as a result we can have the induced current. So in this case, we are changing the orientation of this loop. Okay, so we are changing this angle theta, and as a result there would be change in the magnetic flux passing through the loop, which produces the induced current. So the induced current produced in this way is not constant. It changes with the orientation. So for example, when the orientation is like this, so the face is perpendicular to the magnetic field. So magnetic field is pointing that way, and this surface is perpendicular to that, or you can say the area vector which is perpendicular to the face is parallel to the magnetic field. So when A and B are parallel, area vector and magnetic field are parallel, the flux is maximum. Okay, in this case we have maximum flux, and then here in this case we have a zero flux because there is no magnetic field lines passing through this face. Okay, it's just going through the surface, but it's not actually penetrating the face. And again here we have maximum flux, zero flux, maximum flux. Okay, so the flux passing through the surface is changing with time, and that gives us the changing voltage or changing current. Okay, so at some instant we will have maximum voltage or maximum current. So this could be either voltage or current, and at some other time we can have zero current or zero voltage, and then we'll have negative maximum, and then zero value, positive maximum, and then zero. So this kind of variation in current or voltage is called, or this type of current is called, alternating current. So in the previous chapters we were dealing with the direct current. In the direct current, the current doesn't change with time. So if you have a battery connected to some resistor or a bulb or something, then the current produced by this battery doesn't change with time. So if you plot the current produced by the battery versus time, then the current would be flat. Okay, it would be constant. But here in this case, the current produced by rotating this closed loop is changing with time, so it's alternating current. So the current that we use in our household is also alternating current, and it is produced in large scale at power station. At the power station, they usually boil water, produce steam, and then pass the steam through some kind of turbine, and then they rotate the turbine. As they rotate the turbine will have these closed loops wrapped around some cylindrical object, and the flux passing through the loop changes with time, and because of the change in the flux, that produces the current or EMF. Okay, so this is the way alternating current is produced in large scale. So because the current is changing with time, that means we have different values of current or EMF at different times. So that means if I want to know what is the current at this point, okay, at this time, or if I want to know what's the current at this time, then we need to use a formula that gives us the current at different times. Okay, and the current at these individual times is what we call instantaneous current. So instantaneous current is the current at different instants of times, and it is given by this formula. So I is equal to I naught or I max times sine or cosine. It could be sine or cosine. I will explain that when you write sine and when you write cosine. Omega t, okay, plus phi. So this gives us the instantaneous current at different times. Okay, this t is the time, okay, at which you want to find the current, and this I naught is the peak current. It is called peak current. It is also called maximum current. So the current at this point is the peak current. Okay, so you see what the value of this peak is. That gives you I naught. Sometimes it's also written as I max or I peak. Okay, but they are all representing the same thing. This is also I peak, but this has the negative value. Okay, and this one has the positive value, and this I naught is basically just the magnitude of the peak current. And this omega is the angular frequency. You have seen this in the previous chapter also. It's given by 2 pi f. Okay, f is the frequency at which the waves are produced. So f is basically defined as how many complete waves are produced in 1 second time. In a unit time. So for example, if you produce 100 waves, 100 complete waves in 1 second, then the frequency is 100 hertz. Okay, so one complete wave is the wave from one trough to another trough. Okay, so this much wave is the one complete wave. Okay, or you can also say one complete wave is from this point to this point. Okay, so this wave could also be considered as one complete wave. So That's the angular frequency. And now let's talk about what this phi is. Okay, so this phi is called phase factor, and it is basically, it tells you where the wave starts. Okay, so you have a cosine here. Cosine means it's this wave, but instead of starting from the maximum, if it starts like this, let's see, its maximum is not at the starting point. Let's say its maximum is somewhere here. Okay, now its maximum is a little bit before this much value. So this represents, okay, that this wave doesn't exactly start from the maximum. It starts a little bit before the maximum, or I should say in this case it's a little bit after the maximum, because this point is before that point. Okay, this is the time axis, so this point comes before this point, so this starts after the maximum. Okay, so this phase factor tells you where the maximum is, or at what point the wave starts. Sometimes we can also use sine here instead of cosine. So you can write omega t plus phi. So this is when the wave starts from the minimum value of the curve, okay, like this. So this is the sine curve. When you have curve like this, that's sine. When you have a curve like this, when its maximum starts from the beginning, so that's cosine. Okay. So in this case, you don't need to worry about that, because it exactly started from the minimum value, and here in this case it exactly started from the maximum value, so that's that. Okay, so there is no phase factor. But if it doesn't start from either maximum or minimum, then you will need to add some phase here. Okay, so you will need omega t plus phi, and this phi will tell you where the wave starts from. Okay, so that's the instantaneous current. Now the current that we often use in actual practice is called RMS current. Okay, so there are two types of current that we usually use. One is called peak current. Peak current is the maximum value, so that's the peak current. Okay, so that's the maximum value of this current, because this current has different values, it's changing with time. So the maximum value is the peak current, and often in our daily practice we use something called RMS current. Okay, so this is a kind of average current, but we don't use the average like in the normal way. Okay, so usually when you have to take average of some numbers like 1, 2, 3, something like that, you add the numbers and then you divide by how many numbers you have, so that gives you the average. But we cannot do that kind of average here. If you do that, you'll just get zero, because you have certain part in the positive, certain values in the positive part, and you have the same kind of values on the negative part. You have some values on the negative part here and same kind of value on the positive part. So basically you add and subtract the same values, so that will give your average current of 0. Okay, that means we cannot just use this kind of averaging for this current. That's why we need to use something called RMS averaging, which is called root mean square. So we use root mean square average, or we use root mean square current. So root mean square is basically you take all these currents. Okay, so you have different values of currents. You have like I1, I2, I3, and you have like all these different currents. You square each of these currents, okay, and then add those currents, okay, and then divide those currents by how many currents you are considering. So let's say you have n number of currents you are considering, and then you take the square root of that. Okay, so that's the square. That's what this root mean square value is. So when you do the math, okay, we will not show the math here, but if you do the math, you can show that root mean square, which is denoted by IRMS, root mean square current is given by peak current or maximum current over square root of 2. Okay, so that's the relationship between IRMS and I peak. So this relationship or this kind of graph applies to both EMF or voltage as well as current. Okay, so like I wrote, the instantaneous current as I instantaneous is equal to I max cosine or sine omega t plus phi. Okay. Now this equation also could be applied to voltage or EMF. So EMF instantaneous, meaning the value of voltage or EMF at different instants of time is given by this formula. So E maximum, so maximum value of EMF times cosine omega t plus phi. Okay. Now again, if the curve starts exactly at the maximum, then this would be 0. Okay, and if the curve starts at the minimum like this, then you would express the EMF, instantaneous EMF, as E maximum. In this case, if it starts from minimum, then you will have sine omega t. Okay. So the current that we produce at power station is alternating current, and if we transmit the current produced at the power station in a regular wire, then you will lose lots of power. Okay, you'll lose more than 50% power. So in order to prevent the power loss during the transmission, we will need to use something called transformers. Okay, so basically when you produce the power at the power station, you produce large amount of current, and if you transmit those current to the power to the grid lines, you will lose lots of energy. But we don't want to lose too much energy, so what we do is we decrease the current in the transmission. Okay, so if we could decrease the current in the transmission, then that will prevent us from losing the current, to losing the power. So because we know that power is I squared R, bigger the current or higher the current, more is the power loss. So in order to prevent the power loss, what we need to do is we need to decrease the current. Okay. So the way to decrease the current is by increasing the voltage. Okay. So our purpose here is to decrease current so that we can prevent the power loss. And to decrease the current, need to increase voltage. Okay. And this kind of phenomena is called step up. Okay. And for the step up process, we use a transformer, which is called step up transformer. So you increase the voltage from, let's say, 12,000 volts to 240,000 volts. So you ramp up the voltage. By doing this, you decrease the current, and that's how you prevent the power loss. Okay, so you transmit the power at higher voltage through this high voltage transmission line, and then just before distributing the just before the distribution of the current to the household, you again step the voltage down, because we don't want to supply this high voltage to the household. So you drop the voltage from that to 8,000, and then there is again another relay station here. You drop again to 240, and then just before supplying it to the household purpose, it is decreased to 120 volts. So all this process is called step down process. And for the step down process, you use the step down transformers. So you have two types of transformers. One is step up transformer, which is used to increase the voltage, and you have step down transformer, which is used to decrease the voltage. Okay. Now let's look at the basic idea behind the transformers. So the basic idea behind transformers is mutual induction. We learned about mutual induction in the last lecture. We saw that when we have two coils close to each other, and if we pass some current through this primary coil, to this coil or solenoid, and if we change the current, okay, with time, then there would be change in the flux. Okay, so we know that when there is current passing through this coil, there would be this magnetic field. This magnetic field is due to the current, and if somehow we change the current with time, if the current is changing continuously, that means this would be also changing with time. So changing the current changes the magnetic field lines, and as a result, the magnetic field lines passing through this coil will produce the induced current. Okay, because of the change in the magnetic field lines, there is change in the flux passing through this coil. As a result, from Faraday's law, when we have change in flux passing through some coil, that produces the EMF or current. So there would be EMF or current produced in this coil. Okay, so the coil that we supply the current is primary coil, and the coil which we induce the current is secondary coil. Okay, so we know that the EMF induced in this coil is due to the magnetic field produced by this, or the changing magnetic field of this current. So this phenomena is what we call mutual induction. Okay, so EMF is induced in this coil due to the changing EMF in this coil. So there is this mutual induction. And if we somehow reverse this, like if we supply AC on this side, alternating current on this side, and then put this voltmeter on this side, then we will see that the alternating current on this side will produce the changing magnetic field, and that in turn produces the alternating EMF on this side. So this is the basic idea behind the transformer. So in transformer we have this side, okay, primary side, and the secondary side. So the primary side is connected to the input voltage or input current, and then on the secondary side we get the output. Okay, and the number of turns of the coil is different on primary and secondary side. So depending on whether you want to step up or step down the voltage, you will have different number of turns on the primary and secondary. So if you want to step up the voltage, then number of turns on the secondary would be greater than number of turns on the primary. Okay, the voltage produced depends on the number. If you want higher voltage on this side, then you will need more number of turns on this side. Okay, so this is for step up. Now for step down, if you want to decrease the voltage on the secondary side, on the output side, then you will need the number of turns less than the number of turns on the primary side. So in this case, you have more number of turns on secondary side or output side, and less number of turns on the primary side. So this is step up transformer. Okay, now if I draw something like this, okay, so more on primary side and less on secondary side. So this is NP and this is NS. So this is secondary, this is step down transformer. Okay, so this is the symbol for transformer. We have, this is primary side and this is secondary side. So the voltage you supply on primary side is EP, or sometimes you can also write VP. So that's the primary voltage, that's VP, and the voltage you get on the secondary side is ES. Okay, so that's the voltage on the secondary side, and this is from the Faraday's law. So if you supply the voltage on the secondary, you will get this induced EMF on the primary side. If you supply voltage on the primary side, like here, then you will get this output. Okay, that would be your EMF on the secondary coil. Again, the voltage on one side induces the voltage on the other side. That's why the transformer is said to be based on mutual induction. So if we combine these two equations, we get this equation. Okay, so this equation is what we called transformer equation. Sometimes we can just write V instead of E. Okay, so V secondary over V primary is equal to N secondary over N primary. So voltage on the secondary side over voltage on the secondary voltage on the secondary side over voltage on primary side is equal to number of turns on the secondary side over number of turns on primary side. Okay. Now we can also relate this with the current. So for the current, we can write that. Okay. So voltage and current, voltage and N, okay, are directly related. So primary and primary on the top, secondary and secondary on the bottom. Now for the current, it would be, if voltage is primary on the top, secondary would be on the top for current, and primary would be on the bottom for the current, because to increase the voltage, you need to decrease the current. Okay, so you have current and voltage opposite to each other. So that means if you step up voltage, that means you are stepping down current. Okay. Again, the basic idea here is you either step up the voltage or step down the voltage at the cost of either stepping down the current or stepping up the current. So to step up the voltage, you need to step down the current. And if you want to step down the voltage, you need to step up the current. So that's the transformer equation.